Alright, in this video we're going to be talking about determinants. And the determinant is a real number that's associated with a square matrix. There are several uses for this number called the determinant. It can be used to calculate area in 2 dimensions or volume in 3 dimensions. There are some problems in your textbook that talk about this, so you could check that out. You may have a couple questions in the online homework that reference that as well. It's going to be used also for something called a vector cross product in Calculus 3. So this is a skill that you will use in calculus. That's kind of why it's included here. You'll talk a lot about vectors in Calc 3, and cross product's a pretty common operation to use with a vector. So we'll be talking about that then. Okay, so notice we said a square matrix. That kind of surprised me at first. I haven't looked at these in a while, and I said, what? We can't do it for a rectangular matrix? And I guess not. So only a square matrix. We're mostly going to look at 2x2s and 3x3s, just to give you a chance to see that. And the method is a little bit different for a 2x2 versus a 3x3. So we're going to start with the 2x2 and practice that first. I'm going to go ahead and circle this because it is a square matrix, and that's kind of important. Okay, so the determinant of a 2x2 matrix, here's kind of a general matrix. We've already talked about the name for the whole matrix is usually a capital letter, and then the elements, which will be numbers in the matrix, are usually represented by lowercase letters. So the determinant, you can write in a couple different ways. I think your book uses the DET and then the name of the matrix, so the determinant of A. Some books just use these bars. It's almost like the absolute value bars, sort of, okay? But for a matrix, that can represent the determinant as well. To calculate the determinant for a 2x2 matrix, we're going to multiply the left diagonal, and then we're going to subtract the product of the right diagonal. So A times D minus B times C. So let's try that out. So here's an example from your book. This is number 3. This would be like A, B, C, and D. So I'm going to go from left to right. The left diagonal would be -1 times 3 minus the right diagonal would be -2 times 5. And the determinant is just one number. It's not an array. It's not like some of the things we've done in the past. It's just one number. So this would be -3 minus -10. Really, this becomes +10. So the determinant of A here. Oops. I probably shouldn't have put an equal sign there. All right. The determinant of A is 7. Yeah, I'll just leave it. Okay, so that's for a 2x2. That uses the same process for any matrix of that size. Now let's say we wanted to upgrade, and we bring up to a 3x3, okay, but really the process for a 3x3 could be extended to any larger matrix. So the determinant of a larger matrix, we're going to calculate what's called a minor. There's a lot of notation here, and so I'm just going to go ahead and include that. We won't always use this notation so much for us. We're just trying to be able to find the determinant. But it's good to start thinking about how to represent this process with some notation or with a way to write it or describe it. And that's kind of what this is. So a minor is where I delete row I and column J, and then I find the determinant. Okay, so I have a matrix, We're going to do this in a second, so I won't write down an example here, but we're going to delete a row, we're going to delete a column, and then we're going to put the other elements together as a matrix as if that row and column didn't exist. And then we're going to find the determinant of that resulting matrix. That's called a minor. There's a word for that. Okay. And then the cofactor is a lot like the minor, but when we calculate the determinants of these smaller matrices, we're going to be adding them up. And when we do that, when we add them, they alternate sign. So the first one will be positive, second one negative, third one positive, fourth one negative, and so forth. And so the cofactor, we use Aij, it's the coordinates, where the I is still row I and the J is still column J. And we're going to multiply by -1 to the row plus column power. That's going to allow the sign to alternate, right? Because I'll have even, then I'll have odd, then I'll have even, and then I'll have odds, which would be +1, -1, +1, -1. Okay. And I'm going to add all those up to get the value for the determinant. Not only am I going to add them, this is described in words right here. Let's do that. Okay, I'm going to find the determinant. I'm going to multiply each element in a row or a column by its cofactor. So this Aij right here is the actual element in that row, and then this capital Aij is the cofactor. I know this is a lot of notation, and so if that is lost on you, but you still understand the process, that's really more important than the notation. Okay, and I'm going to demonstrate the process for you in a second. So I'm going to take the element times the determinant of that smaller matrix. I'm going to alternate their signs, and then I'm going to add them up, and that's going to give me the determinant. Okay, so this is all of this description. Number one, it's of course described in your book. Number two, I have this all typed up in the notes that are posted along with this video. And then, of course, you could write it down from here, I suppose, if that's really what you wanted to do. Okay, so let's try this out so you can understand how this works. Let's calculate the determinant of A using this method of cofactors. And you can do this with any row or any column. I'm such a creature of habit. I usually just use the first row. So I'm going to demonstrate this with the first row. Sometimes it's more convenient to use a different row or a different column. And so the process is actually the same. But today we're just going to do it with the first row to get you started. Okay, so I'm going to be using, this is number 11 from your book. Here's matrix A. I want to find the determinant of it. Okay, I'm going to be using the first column as, the first row as sort of my reference. So I'm going to be taking the element of each row, like 1, and then I'm going to be eliminating that row and column, and then taking the matrix that's left and the determinant of that. Then I'm going to do the same thing with the second element. I'm going to take this element, I'm going to delete its row and column, take these 4 elements as a matrix and find the determinant of that. And then I'm going to do that same thing for the third element. I'm going to delete its row and column, take this element times the determinant of the resulting matrix. Okay, so let me draw that out for you so you can see it. I made 3 copies so we could write all over them, okay, so you could maybe get a better visual. And so I didn't have to like try to erase or do it again or something like that, okay? So first I want to take, I'm using the first row, so I'm going to take this element and I'm going to delete its row and column. Okay, so then I'm going to be adding all these things together. So the determinant of A will be that 1 times the determinant of this matrix right here. And I'm going to write that with those absolute value type bars on the side. And then I'm going to do the determinant in a minute, okay, because I want you to understand the process first. Okay, so that's step one. I take the first element, delete its row and column, and then I'm going to multiply it by the determinant of this leftover matrix. Second, I'm going to take the second element in that same row. I'm going to delete its row and column. Okay, remember we said we're going to alternate sign. So most of the time we're going to be doing a 3 by 3. So the first one is positive. It's the second one that changes sign. So I'm going to be subtracting this one, minus 2 times the determinant of the leftover matrix. And this one is like in two pieces, so you have to piece it together. So 2, -2, -1, 1. And then I'm going to do the same thing for the third element. I'm going to delete its row and column. And this one's positive again. I'm going to take the element, which is -1, times the determinant of that leftover matrix. 2, 3, -1, 4. Okay, so that's the process. Now let's finish the calculation so you can see how this wraps up. So that means that the determinant of A, now we're combining what we've just done with the previous example where we did a 2 by 2, where we multiplied the left diagonal minus the right diagonal. I'm going to try to write all that out for you so you can see what we're doing. Again, this is one of those things that I would do the determinant in my head and write down one number here, but I'm going to write it out so that you can see it. Okay, so let's do this. All right, so this will be 3 times 1 minus -2 times 4. Okay, this is the determinant. All right, then I'm going to have -2 times 2 times 1 minus -2 times -1. Same thing. This is the determinant of that. Okay, and then I'm going to have -1 times 2 times 4 minus 3 times -1. That's the determinant. Okay, now we just need to crunch the numbers. So this is really just 1, so I'm going to leave that out now. This will be 3 minus negative, so 3 plus 8, so 11, minus, this will be 2, I'll leave that there for now. This will be 2 minus, this will be positive 2. 2 minus 2, so that's 0. Minus 1, I'll leave the 1 out. This will be 8 plus 3, so 11. Okay, so the determinant of A is 11 minus 0 minus 11, that's 0. All right, it's not always 0, but this one just happens to be 0. Okay, so this is the method you can use to find the determinant of a 3 by 3 matrix. And the process is really based on that row that you choose. I chose the first row, the element of each row, delete the row and column, and multiply that times the determinant of the resulting matrix. Okay, I think I have one more idea here. This is called Kramer's rule, and it uses determinants to solve a system. This is in the same section in your textbook. Okay, so we're just going to use this to solve a 2x2 system. It's very similar to solve a 3x3 system. It consists of, for a 2x2, it consists of calculating 3 different determinants. I'm going to do the determinant of the coefficient matrix, so just the left-hand side of the equal sign. Then this is the determinant with regards to x, and so we're going to do not the x terms, but C and B. I really think these are backwards because of that alternating thing, but I'm not totally sure about that. And then the determinant with regards to y, we would delete the y, right, and just do A and C. Okay, so then the solutions look like this. The determinant with regard to x divided by the determinant of the coefficients, and likewise for y. So let's try this out. This is not something I will ask you to memorize. If I do ask you to use Kramer's rule on a test or any kind of assignment, I'll definitely copy this down for you, because I don't really feel like that's something, I don't know, that might be worth memorizing yet. Okay. All right, so remember this is A1, B1, C1, A2, B2, C2. So we're going to form these 3 matrices and then do their determinants. All right. So let's just write it like that. So this D will be the determinant of A1 and B1, 3, 2, 2, and -1. The determinant with regards to x will be C1, C2, and then B1, B2, and then the determinant with regards to y will be A1, A2, and C1, C2. Okay, now that we've formed the matrices, let's go ahead and calculate the determinants of those. Remember, it's the left diagonal minus the right diagonal. So D itself will be, I'll write it out, 3 times -1 minus 2 times 2. It's -3 minus 4, which will be -7. All right. D with regards to x will be -4 times -1 minus 2 times -5. So that would be 4 plus 10, so 14. And the determinant with regards to y would be 3 times -5 minus -4 times 2. So that's -15 plus 8. So that would be -7. And then we go all the way back to the solutions according to Kramer's rule. So x will be dx, which is 14, over d, which is -7. And y will be dy, which is -7, over d, which is -7. Oops, I'm sorry. So x will be -2, and y will be +1. And that's an x value and a y value, just like we would normally solve a system that looks like this. The point that those 2 lines cross at would be the point -2, 1. And I suppose if you wanted to double check that, you could always solve that system using substitution or elimination just to sort of back this up, make sure that it actually works. All right, well, I hope that gave you a little bit of information about how to calculate the determinant. I think we've said this for the last 3 videos, but this definitely is worth a practice session. So I hope you'll take some time to practice this. If you are using Kramer's rule, remember I said I would provide the rule for you, so you could definitely use that as a reference. That's not something I'm asking you to memorize, definitely not. Best of luck!